Imagine standing on a bridge made entirely of glass, suspended hundreds of feet in the air, in temperatures so cold your breath freezes instantly. Now imagine that bridge starts to shake. Not from an earthquake, not from traffic, but from something invisible, wind. In just seconds, that beautiful glass structure could tear itself apart. This isn't science fiction. This is aerodynamic flutter, and it's the reason engineers are terrified of building glass suspension bridges in subarctic regions. Suspension bridges are engineering marvels. They stretch across impossible distances, held up by nothing but steel cables and physics. But when architects dream of building these bridges out of glass, for stunning views, for modern aesthetics, they run into a deadly enemy, wind-induced flutter. Today, we're diving deep into why this phenomenon becomes catastrophically dangerous in extreme cold climates, and why some of the most ambitious glass bridge projects have been scrapped entirely. Let's break down what flutter actually is. Every bridge deck, the part you walk or drive on, interacts with wind. Normally, this interaction is harmless. But at certain wind speeds, something dangerous happens. The bridge starts to vibrate in sync with the wind's turbulence. This creates a feedback loop. The wind pushes the bridge moves, and that movement changes how the wind flows around it, which pushes the bridge even harder. This is called self-excited oscillation. Think of it like pushing a swing at exactly the right moment every single time. Each push adds more energy. Eventually, the swing goes higher and higher, until it can't take it anymore. With bridges, this energy has nowhere to go except into the structure itself, causing twisting, bending, and eventually, catastrophic failure. Now here's where it gets even more dangerous. Traditional bridges use steel or concrete decks, heavy, rigid, and full of natural damping that absorbs vibration energy. Glass is different. It's lightweight, it's brittle, and most critically, it has almost zero flexibility to safely absorb oscillation energy. When engineers replace solid decking with glass panels for aesthetic appeal, they dramatically reduce the structure's aerodynamic damping. This means the bridge becomes hypersensitive to wind-induced vibrations. Even a moderate wind speed, one that a steel bridge would shrug off, could push a glass bridge into flutter conditions. And once flutter begins in glass, there's no gradual warning. Glass doesn't bend before it breaks. It shatters. So why does subarctic weather make this exponentially worse? Three brutal factors combine here. First, air density. Cold air is denser than warm air. Denser air means wind carries more force per square meter. The same wind speed in -20 degrees Celsius hits a structure with significantly more aerodynamic pressure than in warmer climates. Second, material brittleness. Glass becomes more brittle as temperature drops. The molecular structure tightens, reducing whatever minimal flexibility it had. This means the failure threshold, the point where flutter causes catastrophic cracking, drops dramatically. Third, wind unpredictability. Subarctic regions experience extreme katabatic winds, sudden, powerful gusts flowing down from icefields and mountains. These winds are notoriously difficult to predict and can spike from calm to destructive within minutes. Combine dense cold air, brittle glass, and unpredictable violent gusts, and you have a recipe for structural disaster. History has already warned us about flutter's destructive power. In 1940, the Tacoma Narrows Bridge in Washington state collapsed dramatically due to aerodynamic flutter, footage that's still studied by engineers today. That bridge wasn't even made of glass, and it still twisted itself into oblivion within hours of high winds. Now scale that risk up with a glass structure in subarctic conditions. Several proposed glass bridge projects in Scandinavia and northern Canada have been redesigned or completely abandoned after wind tunnel testing revealed flutter risks at wind speeds common to those regions during winter storms. Engineers determined that the aesthetic appeal of a transparent glass walkway simply wasn't worth the catastrophic risk of sudden structural failure in extreme cold. So next time you see a stunning concept design for a glass suspension bridge, remember, behind that beautiful transparency lies a battle against invisible forces. Aerodynamic flutter isn't just an engineering footnote. It's the reason why, in the coldest, windiest corners of our planet, function must always win over form. If you found this breakdown fascinating, hit subscribe for more deep dives into the hidden physics behind engineering marvels and disasters. Drop a comment. Would you ever walk across a glass bridge in freezing wind? Let me know below. Thanks for watching. See you in the next one.